Hi, welcome to the final calculus tutorial. In today's tutorial, we are going to be looking at practical applications of differential calculus. Calculus, as with all maths, is a very tangible and practical subject. You need to be familiar with the first three calculus tutorials and functions and algebra in order to progress with this tutorial. I want you to start this tutorial by having a go at these on your own. Let's look at the first example that I gave you to do. I said that the profit earned from a hairdressing salon is given as a function dependent on X, the number of employees. The profit function is this function over here. I then asked you to calculate the maximum profit. How will we do that? Now remember that if this is the profit function, it means that our profit is following this type of shape. And I'm guessing our axis is going to go somewhere over there, which means that this is our minimum profit, which also has negative customers, which we can't have, right? So that's ruled out. But this is the balance of our graph. This is what's left over, and this here is the highest point that the graph reaches. So that would be our maximum profit. How do we get the coordinates of that point, the x value, and then the corresponding y value? How do we get to that? Well, let's look at this. What happens to the gradient as it approaches that point? It's positive, but less positive, it's then 0. Right, let's just draw that a little bit bigger. Looking at our gradient here, it's quite a steep positive graph, which means that our profit is increasing. Here, our profit is still increasing, but at a lower rate. At the top of our graph, it's a flat line, which means that our gradient is equal to 0. That is our maximum point, or our turning point, when our gradient is equal to 0. We know this from graph work, so we are going to apply the same concept to real-life application type questions. We are looking in this case for the maximum profit, hence we are looking for the turning point of this graph. How do we get the turning point? When the gradient, given as the derivative of p of x, is equal to 0. The gradient of p of x is going to equal negative 2 over 3 multiplied by 3, which will just be negative 2. X to the power 3 minus 2 is x squared. 2 times negative 6 is minus 12. X to the power 2 minus 1 is 1. Plus 32 is equal to 0. Once I've gotten to this point, I'm then going to divide by a negative 2. This is just normal algebra so that it makes it easier to solve. This will give me x squared plus 6x minus 16 is equal to 0. That means that x plus 8 multiplied by x minus 2 is equal to 0. That means that x is either equal to negative 8 or x is equal to 2. Alright, now remember what I said about that point. Isn't that point going to be there, which is past our y-axis, which means that we're looking at negative employees? Obviously that can't happen, so the only possibility is x is equal to 2. Now we need to calculate our corresponding y value, or rather the profit we will earn when we have 2 employees working. What we are going to do is we're just going to substitute x is equal to 2 into p of x, so we are looking for p of 2. which will equal negative 2 over 3, 2 cubed, minus 6 times 2 squared, plus 32 times 2, plus 40. Please, ladies and gentlemen, you don't have to go through this long calculation on your own. You do have very advanced calculators. Punch it straight into the calculator, and that will give you an answer of 74.67. Now, I did not give you any parameters, whether it was per day or per week or per hour or anything like that, so you just need to leave your answer as is. If I had to say that this was profit in thousands per month, you would then have to say 74,670 Rand per month. But like I said, I did not give you any parameters on this one. The second one I gave you to do said that the amount of bees in a beehive at a particular point in time is given by the function minus 6t squared plus 20t plus 750, where t is the number of days. The first question I asked was, at the start of the beehive, how many bees are there? Basically, how many bees are there when t is equal to 0? This is easy to do. I'm simply looking for b of 0 is equal to minus 6 times 0 is 0, plus 20 times 0 is 0, plus 750. That means that there are 750 bees at the start of a hive, or rather 750 bees according to this model would be required to start a hive. Wonder who counted that. 2.2. How many after 10 days? After 10 days, meaning when t is equal to 10. That means we are looking for b of 10 is equal to minus 6 times 10 squared plus 20 times 10 plus 750, which will give us an answer of 350 bees. Notice something, that the bees actually dropped. You will see in the next example that the bees actually go from 750 to a maximum amount. They then start to wither away. 2.3. I asked, when is the maximum amount of bees reached? Now, interpret this question carefully. When is the maximum amount reached? I am looking for when. That means I'm looking for a time, a period in time, a day when the maximum amount of bees are reached. I'm not yet looking for the maximum amount of bees. I'm merely looking for the time at which the maximum amount of bees are reached, similar to the previous example where I looked for the maximum amount of employees which will yield maximum profit. Alright, in order to get that, I'm basically looking for my gradient b dash t equal to 0. My gradient is going to be given in this case by negative 12t plus 20, and that has to be equal to 0. That means that negative 12t is equal to negative 20, t is equal to positive 20 over 12, which is equal to 5 over 3. So at the point 5 over 3 days, or 1.67 days, right? So just under 2 days, the maximum amount of bees are reached. The next one I asked 2.4, and notice they all will usually follow this type of progression. 2.4, I then ask what is the maximum amount. If the maximum days, or the point in time where we have maximum amount of bees is given as 5/3, wouldn't the maximum amount of bees be given by the function b of 5/3, which will equal -6 times 5/3 squared plus 20 multiplied by 5/3 plus 750, which will yield an answer of 768. It's not a whole number, it doesn't work out to a whole number, but if you round it off, it comes to more or less 768 bees. And that is the maximum amount of bees that will be reached. Number 3 says that the number of shoppers in a shopping mall depends on the number of shops, and that's given by the function number of shoppers as a function of shops is equal to 4x squared minus 160x multiplied by -2000. The first question I asked was how many stores should there be, how many X's, how many stores will yield a maximum amount of shoppers. So 3.1, maximum amount of shoppers are going to be given by the optimum amount of stores. Optimum amount of stores are given by S dash X, or the gradient of S of X is equal to 0. In this case, the gradient is going to equal 8x minus 160, 8x minus 160, and that has to equal 0. That means that 8x is equal to positive 160. That means that x is equal to 160 divided by 8, which is 20 shops. 20 shops would yield the maximum amount of shoppers. Now I ask, what is the maximum amount of shoppers? Basically, I'm looking for the amount of shoppers that will come about when we have 20 shops. That will be S of 20, which will equal 4 times 20 squared minus 160 times 20, all of that multiplied by -2000, and that will give us an answer of 3,200,000. Obviously this is a bit of an obscure example, but you get my drift. The fourth one I gave you to do came slightly out of the 2008 GDE final. The reason I say slightly is because I had to manipulate this to make it something that was workable. I included this to give you more of an idea of what to expect from your final exam in terms of application calculus. Notice that it's quite an easy one. It started off by giving us a triangle with sides x plus 2 and 3 minus x. Also, it's a right angle triangle. And they asked us, show that the area as a function of x is given by -1/2x squared plus a half x plus 3. They followed that by asking for the maximum area. We're going to start off by trying to get our area to this year. I know that the area of any triangle is given by a half base times height. We can very easily say that this is the base and this here is the height because they're perpendicular. That means that the area of this triangle is equal to a half times by the base, which is 3 minus x, multiplied by the height, which is x plus 2. That's going to give us minus x squared plus x plus 6 all divided by 2. Once I've got that, all I need to do in order to get my area into the function that they asked it for, I'm just going to split all of these up. X squared over 2 is going to be negative a half x squared plus x over 2 or plus a half x plus 6 over 2 or plus 3. And that is what they asked for. To work out the maximum area, 4.2, maximum area will be given by the derivative equal to 0. Remember, this here is a graph that looks something like that. Actually, that would be on the other side. It's a graph that looks something like that, which means that the maximum area, our area increases to a point and then starts to decrease depending on my different x values. We are looking for that point, which is when the gradient is equal to 0. The gradient is equal to 0. That means my gradient of this is going to be given by minus 1. 2 times minus a half is minus 1. X plus a half is equal to 0. That means that minus x is equal to minus a half. That means that x is equal to positive a half units. This is only my x value, which gives me my maximum area, but my maximum area is given by area as a function of the x value that gives me my maximum area, which is equal to negative a half multiplied by a half squared plus a half multiplied by a half plus 3, which will yield an answer of 3 and 1/8 units squared. Again, this one here I did not give you any parameters, whether to use meters or centimeters or anything like that, so you'll just say units squared. Units squared meaning any units that are available to you. Alright, quite an easy one. Number 5. We have to fence off a rectangular area for a specific type of plant against an existing wall. We only have 20 meters of fencing. What is the maximum area we can achieve? Now, with examples like this, I always want you to draw out what's happening. This is the existing wall that we have. We are going to be putting our fence in a rectangular shape over here. Alright? I'm going to start by calling this side X. I don't know how long that's going to be. I'm going to probably be trying to work that out eventually. But I'm going to start by calling that X. Because it's a rectangle, the opposite side is also equal to X. I've got X, I've got X. Remember that I only have 20 meters of fencing available, which means that this side is going to be 20 minus x, or 20 minus 2x. That plus that will equal 20, because I've only got 20 meters of fencing. My area in terms of x is going to be given by length times breadth, which is 20 minus 2x, length times breadth of x. Which means that my area in terms of x is going to be given by 20x minus 2x squared. Maximum area is what I'm looking for, which means that I am looking for my x value when my derivative is equal to 0. My derivative in this case will equal 20 minus 2 times 2 is 4x, and that has to equal 0. Let me just write that over. That means that 20 minus 4x is equal to 0, means that minus 4x is equal to minus 20. Let's just go on to this side. That means that x is equal to negative 20 over negative 4, which is positive 5. If x is equal to 5, I'm going to achieve my maximum possible area. What is my maximum possible area? It's going to be my area in terms of 5, which will be 20 minus 2 times 10. 2 times 5 is 10. 20 minus 10 is 10 multiplied by 5 is equal to 50 meters. 50 meters squared. That is my maximum possible area. Number 6 reads, if fuel consumption of a car is given by Cx is equal to 0.01 multiplied by x minus 80 squared plus 6, where x is the speed we are doing in kilometers per hour, C of x is the actual fuel consumption in liters per 100 kilometers. I am asking 6.1, what is our optimum or most efficient speed? Basically, I am asking what is the speed at which we have the lowest consumption. Lowest consumption or lowest C of x, same thing. And I'm looking for the x value because I'm looking for the speed, looking for the x value. So that will be when my derivative is equal to 0. In this case here, I'm going to have to first multiply. First I'm going to have to square this bracket using FOIL, whatever you want to use. And then I'm going to have to multiply that in. That means that C of x is equal to 0.01 x squared minus 1.6x plus 70. And this is my actual consumption function. C dash x, my derivative, is equal to 0.02x minus 1.6, and that has to equal 0. That means that 0.02x is equal to 1.6. That means that x is equal to 80 kilometers per hour. That means that according to this function, a speed of 80 kilometers per hour would yield the optimum or the most efficient fuel consumption. I then ask 6.2, what is our maximum consumption? Basically, we are looking for our consumption, not our derivative, our consumption at 80 kilometers per hour, which will equal 0.0180 squared minus 1.6 multiplied by 80 plus 70, use your calculators, will give you an answer of 6 liters per 100 kilometers. In this question here, I did give you parameters. I did say that the speeds are in kilometers per hour. I also said that our consumption is in liters per 100 kilometers. So all of your answers have to depict that. Number 7 says that we have a cylinder that has to accommodate a volume of 300 milliliters. We are looking to minimize its surface area in terms of R. So we are looking to manipulate R to get the minimum surface area of a cylinder that will carry 300 milliliters of liquid. We are going to start off by looking at surface area. Now of this cylinder, there are three different surface areas we are going to look at. First, let me just run through very quickly what surface area is. Surface area is the outside area of the cylinder. Why would we want to look at surface area? Well, if we are a company that's manufacturing cans, for example, we want to minimize surface area so that we can minimize our cost, but we still want to hold a certain amount of volume. In this case, there are three surface areas. I'm going to call it 1, 2, and 3. The first surface area is the lid, which will just be the area of a circle. The second surface area again is the same type of circle, same size, hence same area. The third shape, most people think of as being something that's round. But think about this, if this is a can and I cut off the lid, I cut off the base, and I make a cut down the middle, and I unfold that can, wouldn't it give me a rectangular shaped figure? Yes? With H being one of the sides, or rather two of the sides, and my other side being, what would give me the distance of that side? Now think about it carefully. It was rolled around the base. So wouldn't that side be given by the perimeter of one of these circles? Remember, a perimeter is basically the distance of a circle from a point to that same point going right around the circle. What gives me perimeter? Perimeter of a circle is equal to 2 pi r. That means that this distance here is given by 2 pi r. That means that the total surface area of this cylinder is going to be given by 2 times the area of the base or the height. So it will be 2 times by the area of one of them, which is pi r squared. Remember, this is the area of a circle. That's the area of one of them multiplied by 2 because I've got the base and the lid. And I've still got to add the surface area of this here, which will be plus length times breadth, which is 2 pi r times h, which I'm just going to leave as 2 pi r times h. Now all of this is fine except for this h. Having this h in here makes it impossible to differentiate. It makes it impossible to find an r value. But remember, I did tell you that volume is equal to 300 milliliters. Now this brings us onto an interesting calculation. Volume, isn't that equal to area of base? Area base multiplied by height. Area of base is the same as that, which is pi r squared, multiplied by height has to equal 300 milliliters. Doesn't that mean that h is equal to 300 over pi r squared? Can't I plug this into here? Plugging that h in, it's going to give me a formula. Area in terms of r is equal to 2 pi r squared plus 2 pi r. Instead of h, I'm going to say 300 over pi r squared, which is going to equal 2 pi r squared plus 600 over r. 600 over r, because 300 times 2 is 600. The pi's cancel, r cancels with one of the r's. This is my area in terms of r. To find my minimum surface area, remember this graph is a graph that's going to look something like that. Minimum surface area is that turning point, which is when my gradient is equal to 0. My gradient of this calculation is equal to 4 pi r. 2 times 2 is 4, 2 minus 1 is 1, 4 pi r minus 600 over r squared, and that has to equal 0. Minus 600 over r squared, because 600 over r is the same as 600 multiplied by r to the minus 1. Minus 1 times positive 600 is minus 600. Minus 1 minus 1 will give me minus 2, which takes it to the bottom. Manipulating this formula, I'll get r cubed is equal to 600 over 4 pi. Because I'm multiplying everything by r squared over 1, r squared over 1 multiplied by that will be 4 pi r cubed minus 600 equals to 0. That means that 4 pi r cubed is equal to 600. That means that r cubed is equal to 600 over 4 pi. That means that r is equal to the cube root of 600 over 4 pi. That, using your calculator, cube root of 600 over 4 pi will give you an answer of roughly 3.63 units rounded off to 2 decimal places. This is not our optimum surface area yet. This is the r value which will yield the optimum surface area. Surface area is given by A of r. So we are going to be looking for A of 3.63, which will give us our optimum surface area, which is equal to 2 pi multiplied by 3.63 squared plus 600 over r to the power 1, which is 300 over 3.63, which will give us an answer of 248.08 units squared. This is our optimum area that can hold 300 milliliters of volume. And that brings us to the end of the 4th tutorial in calculus and to the end of the calculus section. As always, I've left an exercise for you to do in the workbook. Just a quick word on calculus. If ever you were looking for a reason why you had to study maths, calculus is it. In order to do any of the practical examples we have covered in this tutorial, you needed to be able to do differentiation. In order to be able to do any differentiation, you needed to have a solid understanding of algebra and functions. In essence, the practical application of calculus is the summation of algebra and functions.